Thank you very much. I'll now welcome our panelists, Zoran, Neil, Harry, and Phil to the stage. Thank you. So this panel session is obviously interactive. We'll have some microphones around the room as well. But if you'd also like to scan the QR codes here, you can send some questions that will come to me directly if you want to say something or comment or query anonymously as well. So please just download the Slido app and join with the QR code and the code on the screen. Okay, for those who don't know me, my name's Alison McQuillan. I'm Director of Rock Science based in Australia. My background is mining and rock mechanics, and I've been with Rock Science this is going on my 9th year. So a great company to work for. And thank you for joining us in Sydney. On stage with me today is Phil. Phil's Director of Giraffe Mining Consultants. Many of you know Phil from the mining industry. So Phil's background spans over 30 years in civil and mining engineering experience. He's worked across 15 countries in a suite of commodities. He's held senior engineering positions in consulting roles with Golder, Snowden, Rio Tinto, De Beers, and Anglo American. And he's co-authored over 60 international papers. Next, I'd like to introduce you to Zoran. Many of you would have sat in on Zoran's talk in the previous session. Zoran is CEO of GeoRock Consulting. He's got a PhD in mining rock mechanics and over 15 years experience in academia and industry. Likewise, he's published over 60 scientific and technical papers. I'd also like to introduce you to Harry. Harry is the father of the anisotropic ARMR. If you haven't read any of his papers, please take this opportunity to discuss with him as he's travelled from Greece to be with us today. Harry is CEO of Geocon, and he's also a lecturer at NTU in Athens. He's over 25 years experience in civil and mining projects. And most recently, he's been honoured with the 2025 Franklin Lecture from the ISRM. So if in Norway later this year, please catch Harry's speech.
Should.
And finally, I'd like to introduce you to the chair of the ISM committee, Dr. Neil Barr. Neil is Director of Gecko Geotechnics. He has a PhD in rock slope engineering. He's got over 15 years of experience in civil and mining projects, worked in over 15 countries, over 6 continents, and has published 80 internationally published papers. So I'll now hand over to Neil to introduce the committee, and then we'll start with the panel discussion. Thanks, Neil.
Thanks, Alison. So this commission was formed about 2 years ago. Could we go to the next slide, please? To look at risks and reliability in rock slope engineering. And today I was lucky to chair a session just on the right-hand side here. And Vadim Luchnikov, I don't know where he is. There he is. Basically covered this topic in his presentation. It was a fantastic presentation on exactly this. So really what this commission's been made for is to provide a forum for sharing knowledge and ideas and to find ways of reducing the uncertainty that we have in the industry. And the main ultimate topic really is to develop a set of guidelines for both civil and mining engineering on how we can tackle that issue of reducing uncertainty and therefore risk.
Great. Thanks, Neil. Don't forget to send in your questions via Slido.
Yeah.
I'm going to start asking a broad question to the panel. Okay, Neil, you just spoke about the scope. How would this scope be linked in terms of managing data uncertainty related to risks during design with actual risks during execution, and to the panelists with civil and mining application? So, Phil, would you like to start?
Yeah, stop.
Yeah.
I was trying to delay my answer as long as I could. I suppose one of the key parts of that question is what's the tolerable risk profile? And I think certainly from a mining perspective, there's a lot more scope in terms of defining what the tolerable economic risk might be. And Vladim's presentation earlier touched on many of those elements. But I suppose taking a step back, that fundamentally the safety element is not negotiable, and those safety imperatives need to be successfully achieved. The latitude around the design acceptance criteria and design reliability is on the economic consequences and how much effort you want to apply in developing a robust design. So in terms of what the ISRM Commission, well, my understanding of what we're shooting for here is some broad guidelines on processes that can be applied to come to a reasonable, defendable outcome.
Thanks. I might go to Zora now. You spoke about variability in your presentation. How does the variability relate to uncertainty, and how do we manage that risk?
Okay. First, I would like to ask a question to audience. Do you use a reliability-based design in like everyday practice, or you stick to the deterministic approach? Okay, let's be honest.
Maybe we can go a show of hands. Who uses routinely?
So do you use probability of failure to...
It's in our software.
Yeah, and also it's easier for us to give questions. So, could you repeat the question, Alison? Sorry.
No, you were speaking about variability in your presentation before. Obviously, variability in model.
So we have like 3 types of uncertainty. So one is model uncertainty, another is parameter uncertainty, and also human error or uncertainty. Probably the most difficult uncertainty to assess is actually human uncertainty, because it's involved in all kind of other uncertainties. And this is something that I think we as civil, geotech or mining engineers should work on in order to upgrade our knowledge regarding probability, statistical analysis, things like that. So we can use this approach like easily in practice. With regard to model uncertainty, I think that it's very also difficult to assess it, but maybe Neil would help me in this.
Sure. So if you've seen any of my online stuff, all models are wrong, some are useful. So we need to, if we come back to Professor Vasilis Marinos's keynote this morning on involving GSI and tunneling, he stressed that between a rock mass or geotechnical model, we need to evaluate what failure modes could happen, then do stability analyses. The same, I think, applies in rock engineering. And the more we can find out about our geological and engineering geological conditions, the more we can rule out certain failure mechanisms and guide ourselves in the right direction for what we should be analyzing, and thereby reducing risk in a sort of qualitative way. Harry, maybe you got some thoughts?
Thanks, Neil. I want to combine 3 different people's views on this topic of uncertainty. One is from yesterday, Professor Poulos. He mentioned that the complex models should be checked with simpler models, which is in fact what we need to make things simple sometimes, to understand the complex conditions, and that's something that we forget. And of course, uncertainty in simple models is relatively low, but in complex models, uncertainty is higher. So it's better to always do this back and forth and check how much uncertainty we allow in our models. Then from Professor Marinos, this, as Neil mentioned, the complexity of the geological model. I mean, sometimes we can have very difficult conditions, very complex conditions. We have to take this into account from the very early on. So that's something that we need to consider, because sometimes we forget about this when we proceed with our modeling. And the third very nice presentation from Vadim this morning was like, for these 3 factors, uncertainty, structural model, parameters, and human, there is a weighting of its factor. And for a model which was very complex, he presented that the structural model can be up to 60% weight out of the total. So I think it's very important to understand the weight of each component, let's say, in terms of uncertainty, and be flexible in this back and forth from the simple to the complex and back and forth, just to make sure that we finally understand the uncertainty. I don't think we have a real appreciation of uncertainty. That's my point. Yeah.
Thanks, Harry. Any questions or comments from the audience so far? Paul, before we come to Paul, we've got microphones coming. But Phil, you spoke about risk, and I believe everyone's got a different risk appetite. Would you want to comment from your experience between how the civil industry typically manages risk or versus the mining industry?
Yeah, I suppose the civil engineering industry, you're designing for public risk, and the appetite for risk is very low. Whereas in mining, obviously, it's a user-defined appetite. But also, I think there's maybe some misconceptions around the 2009 guidelines defining factors of safety and probability of failure for open pit mines. Those were never meant to be prescriptive sets of criteria. If you read the chapter in detail, there's sections there that each mining company needs to define what their risk appetite might be, and a junior mining company compared to a tier one mining company have got completely different risk profiles and expectations. So those guidelines, and they are guidelines, they're not standards, need to be taken with a pinch of salt and, I suppose, adapted to your specific applications. And back to Zoran's comments around risk-based design, the input parameters, the confidence and consequence needs to be factored heavily in those outcomes.
Thanks, Phil. Paul?
Yeah, so the question was asked, how many of us use probabilistic methods? And Ali hopped in to say that it was available in the rock science software, but so often we're data deficient. In the view of the Commission, is it adequate to substitute engineering judgment literature for coefficients of variations of the various material types that we're going to be included in our stability analysis?
I might start with this one and maybe Zoran after. So I think if you're very data deficient, it may not be realistic to do probabilistic immediately, and there'll be a second phase of a project. But in that case, you can look at reasonable lower bound values for certain parameters based on the situation. So if you're in a weak rock mass, perhaps a 20th or 25th percentile UCS strength. If you're in a strong rock mass, looking at the jointing in more detail, looking at more sensitivities around that. So you could start with the sensitivity analysis or parametric approach until you had sufficient data to do probabilistic. Zoran?
Yes, just to add, I think that around, let's say, 30 samples is needed in order to perform high-quality probabilistic analysis. But, for example, Eurocode proposes the minimum 2 samples. So by means of 2 samples, you can apply characteristic values, determine characteristic values and things like that. So, but then you actually have higher coefficient of variability, higher uncertainty, and this is accounted for in probabilistic stability analysis. I also maybe want to ask one question to the audience. Do you understand what does the probability of failure of 10% means? So, and how do you look at it? When we speak about factor of safety 1.45, 1.1, it's understandable. But what does the probability of failure of 10% means?
It's really the 10% you mentioned, 10% of the total number of cases analyzed, and we do be fly below that percentage that you choose.
Exactly. And in, for example, mining engineering, going from the bench scale to the larger scales, we have those different probability of failures according to the LOP guidelines. So up to the 50% for bench failure is acceptable. In civil engineering, the sector I'm coming from, probability of failure of around 0.1% is barely acceptable, you have to go below it. Because we have structural measures involved, so for example, anchors, piles, and these structures cannot maintain uncertainty. So only small displacements and things like that. So we have to be much more precise when modeling civil slopes. This is also something that has to be considered, and the task of our commission is to make comparisons between civil and mining engineering. So to put all together and to give some kind of recommendations for the future.
Thanks, Oren. I'd also add, if you're very data deficient, then there's lots of uncertainty. So we can't just do a single deterministic analysis. As Neil said, we need to do some type of sensitivity. If all you've got is literature, that's something to go on, but you would clearly need to state that it's not a site-specific data set and further analysis will be required. But yeah, I think from Harry's speech yesterday, everyone's dealing with not as much data as they'd like in many projects that we're working on. I'm going to hand back to the floor if there's any other comments or queries for the panel.
I want to make it comment.
Please, Dr. Verman.
Thank you. Talking about some of the things we discussed, civil mining and data uncertainty, data deficiency, in ground conditions where you have frequently changing geology, such as my part of the world, I come from India, the Himalayas, one of the toughest tunneling media, if you can call them. And so even with, although it's always data deficient because of many reasons, but even for the site-specific investigations, you often get a wider range of each of those parameters, and then you would perhaps be, advised to do a probabilistic analysis, because instead of just analyzing one deterministic case, you are analyzing maybe 10,000 cases, and so that's where it works. Plus, we sort of need to cover it with monitoring, because one is still never sure how the nature would respond to the intervention. We put a tunnel or cut a slope or make a foundation. So monitoring is something which is neglected. So in countries like India and Nepal and countries like those, these are neglected parts of covered monitoring coming. But in between, you have the model, and therefore models from rock science, for instance, they have this sensitivity analysis was mentioned. You pick up the factors which are going to influence the design the most. You pay more attention in investigation, and those do probabilistic analysis, even with the site-specific data. And then of course you do the monitoring and you do that. But and civil and mining, the thing about mining is, yes, the appetite is more for risk, but at the same time, many of these mining operations are strictly controlled by, in India, for example, Director General Mine Safety, with strict rules. Okay, you do this and just this, and so not so much in civil, but in mining. Like in civil, most of the risks I've seen in the Himalayas and in my country is during the construction. Now, in mining, you're always constructing, you're always operating the mine before you close it. So mine under operation and civil engineering project under construction, and similar in risks as well as that is concerned. Mining, the risk sometimes can be greater from the owner's perspective, because any failure, and these days with the media trying to get any bite from anywhere, can straight away affect the commodity price of the stock market, and can set the company back a lot. So it's a situation which is, as was mentioned, that it's a site specific and a project specific and maybe company specific, even to the commodity specific thing as far as mining goes. So those are some of the comments I wanted to make.
Thank you for your contribution. I've got some questions coming in from Slido, so keep using the app. Thank you. Okay, when monitoring data is acquired during the course of a project and it doesn't match the model, what measures should be taken to address this issue?
Well, I guess that's when things get interesting. So usually that's a really good sign that you should be a bit more inquisitive and trying to find out what's going on. So, beginning with perhaps with the site inspection, mapping, drilling, trying to find out the mechanism that's at play, and then trying to replicate that mechanism in a model. Harry?
On this aspect, I think some of the inconsistencies that could be on the model that was assumed could explain this significant difference in the monitoring or parameter selection. Right, rock mass parameters could be, for example, lower strength or, different rock mass classification in terms of range of values considered. I want to add also that the observational approach, which is not related, of course, with this question, but as a general approach, sometimes, at least in civil engineering, we might use it to make our designs more economical. So that's another aspect that we could consider when we are dealing with uncertainty.
Is this something the panel would consider as a checklist on, as I guess, mining and civil construction progresses, analysing monitoring data, and then as not just a design, leave it and forget about it, come back and do a continuous check, something you build into guidelines?
Yeah, I put monitoring in the same category as reconciliation. And so in whichever way you're going, or whichever data you're looking at, that the tolerances on the design need to be well defined according to what the key failure modes are. So I'd be expecting that the monitoring system is focusing on the early onset of those key uncertainties and the primary modes of instability. And I mean, with those monitoring programs and reconciliation programs, you're either going to get three outcomes. Either it's about what you're expecting and keep going, or it's better than what you're expecting and there's opportunity to optimize, or it's worse than what you're expected and you need to go back to the drawing board and refine the design to cater for the new found conditions.
Thanks, Zoran. Harry, any comments there? I can move on.
I think Phil covered that very well.
So you're obviously involved in many geotech review boards as well. Where have you come across instances where the modelling doesn't match the failure mechanism, and also potentially a better material model could have been applied? And any feedback to the audience or suggestions there?
I might start this. I think, look, a lot of companies sometimes fall into the trap of creating a procedure to do this task, and then sometimes that removes thinking. So I've noticed a lot around various countries in the world in the last sort of 12 to 24 months, rock slopes being designed using two-dimensional limit equilibrium analysis, which is fine, but looking for circular failure. Now, Alison, you and I did a study on some 500 slope failures a couple of years ago. Less than 10% were circular failures in rock slopes. So we're not always analysing for the most realistic and correct failure modes. Sometimes these things are falling through the cracks. Harry, what about you in perhaps in civil?
Yep. I have an example from civil engineering where the practical approach was to design the project with limited data, and they allowed for more or less very conservative design. In practice, what they realized with this conservative design, they have over-designed, and comes from a project. It's a mega project, actually. So imagine what implications it has for cost for a project when you are designing, depending on the area. If it's a civil engineering project in a remote area, sometimes could be limited data. So you are practically allowing for some conservatism in your design, and then finally your design becomes very expensive. And when the time comes to review your design at a later stage during construction, you need to take actual measures, which means that you need to implement a very abrupt change to your mitigation measures so that you are literally reducing the costs. So I've come across this case, which is something that I think most of you might have come in a similar situation. I don't think there is enough space when we have limited data to work with in terms of minimizing costs and so on.
Thanks, Harry. Dr. Yuku?
Very interesting discussion. Because when we are back to what Neil was saying, when we think about risk and reliability, we always link it to as if only for material. And we think about it as if let's change the material normal distribution and move on, and let's look at the probability of failure. It's bigger than this, right? Because material is one item of the whole modeling analysis. You have boundary condition, you have a groundwater analysis, you have a geometry, you have geology. How do you see all this fits in this big picture? Because as if we're looking at material variation, but this is one item. what's the committee think about this?
So one of the biggest challenges is how do we deal with the rogue singularity? So a geological fault in an awkward orientation that we didn't know about. And that's something that we're still working around, but I think there has to be a real link between, as Vasilis Marinos this morning was saying, having a more robust geological model to begin with, and linking that into the ground model from an earlier on stage. But that's one of the key aspects. I mean, if you look at total probability of failure, you also need to consider what if there's a geological structure somewhere that you don't know about, and how do you deal with that? And that's still something that I don't think we have a real good grasp on.
Maybe, Harry, your comments from an academic point of view, if it's more just the knowledge that we have to include all those different considerations, not just vary material parameter in the model.
Yeah, I think it becomes quite complicated to be able to take into account all these parameters changing at the same time. But I think a sensitivity study, similar to what Neil mentioned, to delineate which parameters are more impactful on the final result. For example, if we consider, let's say that the groundwater data that we have are limited, and we have a record that potentially doesn't give us a full picture, we could be doing a sensitivity analysis for groundwater, allowing only this to change and then all the other parameters remaining the same, or then combinations of groundwater and one other parameter, strength parameter, changing, just to see the real impact on the final result on our probabilistic or deterministic analysis. Again, I think another thing is whether we are very confident sometimes that we know all our different components of the problem, and whether we can early on request additional information before we start doing modeling. And so I think it's an iterative process that we need to, or also based it on we can base it on experience from previous studies, and the assumptions can be based on previous experience sometimes. Another approach that is very, I think, important is the return period of, because now we have codes that define the return period of certain, let's say, impacts. Like, for example, earthquake. We have design codes now, long time ago, but now we have more robust design codes. So we may need to make sure that our codes address all these issues and give us a range of solutions, at least for civil engineering.
Just to continue on the discussion, sorry, I don't want to. It goes back to the same thing, is I can use risk and reliability for a wrong model and just to show that I did it, while you're solving, for example, a 2D wrong failure mechanism. And is that enough that I give a risk analysis for a 2D that is not mimicking the real problem? So what's the point?
No, absolutely not. It's not enough. And that's part of the point of all of this is to make sure part of the guidance search is to get people really thinking about what are the engineering geological conditions that we're in, what kind of failure mechanism can we potentially get, and then to start going through the analysis process and looking at enough variability in all of that to see what the risk sort of is, and qualitatively or semi-quantitatively acknowledging that, and then putting some sort of controls in place to mitigate that risk. If we have a 3D problem, absolutely we have to solve it in 3D.
May I add something? So yeah, regarding the creation of the model. So we start from the ground model, and then we come to the geotechnical model. It's a kind of simplification in civil engineering industry. But with regard to, for example, Eurocode, there are these parameters called geometrical properties that you can use to adjust your layer thickness, maybe the fluctuation of or water pressures or the piezometric line. So basically you can apply probability also to, let's say, geological boundaries and the water level that was measured through some period of time. So yeah, it's possible, but anyhow, when we create the geotechnical model, we have to be conservative, we have to be very careful, and basically the things we do, we play with parameters. So this is the main uncertainty. I agree with you completely. So, and I think also I admire Neil's work and Alison's on 3D modeling, but I think that this is very important issue, but maybe these parameters actually are more important issue in everyday design. I mean, compared whether is it 3 or 2D, because 3D modeling is usually non-conservative, so you obtain higher factor of safety value and things like that in a forward analysis. So this is also something that we need to take care of.
I think the outcome of the guidelines should be a broad workflow of elements to be considered rigorously, understanding the geological environment, the engineering geology environment, the design demands that are required, the service life, all of those parameters. And so I don't think we're looking to come up with a prescriptive how to do this. We're looking at a broad workflow that raises the elements, like Alison was mentioning, maybe it's a checklist of things to be considered and have an answer for each of those elements or reason why you're crossing off, why you don't think you need to do a 3D analysis. But it's that broad understanding is a much better outcome rather than having a prescriptive how-to that tries to cater for every eventuality. That's not going to be possible to land on.
Thanks, Phil. Keen to get your thoughts on this question that's come in from Slido. The probabilistic methods may de-risk open pit slope design, but it potentially costs more to implement such a design because of added conservativeness. Your thoughts and comments?
Yeah, good question. I suppose I've migrated away from doing probabilistic analyses in most open pit designs other than for bench design. I think to have statistically relevant data to apply to open pit design, if you're moving beyond single double bench scale instabilities, I think you're starting to ask a lot of your data. And maybe if it's a rock mass model or a isotropic material, maybe you can scale that up to interamp and overall scale designs. But the reason why I say I'm not using probabilistic designs for interamp and overall scale is the stuff we were talking about earlier. The structural model uncertainty plays such a big role that to try and do a probabilistic analysis with uncertain structure, we're fooling ourselves. You come up with probability of failure, pick a number, 1%, 20%, 50%. If the fault's there, it's 0. If the fault is not there, it's 0. Sorry, it's 0. If the fault is there, it's 1. So I don't think it really adds a lot of value on the macro scale to try and present the probability of failure on a overall scale.
If you did have enough data, and to the rest of the panel, do you think it does add an additional cost, be it in time or financial? Zoran?
Actually, I think not. Maybe you need to have a little bit more knowledge in probabilistic analysis. And yeah, for example, 2D modeling lasts for like few 3 minutes, depending on the model. But for 3D modeling, I believe that it will take a lot of time depending on the number of iterations that you have to come to some probability of failure. So yeah, it can take time, but not your, let's say, resources if you have this kind of knowledge. And it is also wise to include all the data you have. For example, 15 3-axial tests or 15 direct shear tests. Why not include it? You will be closer to the truth. Whether the model is right or wrong, you can apply something, you can do something in order to try to increase your reliability. So,
Neil, Harry, any comments before I move on?
I agree with Zoran in terms of if you have the data, if you have a large amount of data, in terms of resources, then it's a decision of how many analyses you require to a proper probabilistic. So it's a balance between the amount of time and resources but definitely would be beneficial, I think.
Yep. Again, agree with the colleagues here. But coming back to the purpose of the commission, it's to address risk and reliability. And just from that risk side, you might not need to do probabilistic. It's a nice to have, but you could do some, especially if you're using 3D modeling, slide 3, RS3 or FLAC 3D. It might not be practical to run probabilistic. It might be more practical to run some reasonable lower bound inputs or increasing pore pressures due to rainfall or something like that. Looking at situations that may occur and trying to understand what impact they could have and then putting in countermeasures against it, whether it's a design change or depressurization or whatnot.
Thanks, Neil. A couple of nice questions coming in from Slido. I'm going to combine two together. So, can surrogate models help improve risk and reliability analysis, especially when dealing with limited data and complex computations? And then on the flip side, do you think there will be an over-reliance on AI rather than engineering judgment in the future? And that, in turn, reducing our understanding of risk. So, comments on surrogate models assisting us, but then will there be an over-reliance on AI going forward?
Harry, Suran?
I can start if you want. I would start with AI, and I would say that definitely AI will be playing a role in what we are doing currently in our workflow in terms of processes and so on, in our modeling and data manipulation and so on. The thing is that we need to make sure that there is a first pass, second pass assessment of the results of AI machine learning processes, and we have to be sure that we appreciate whether there are any mistakes in this process. So that means that we need to have some guidelines, again, for AI. For example, with machine learning, we can do so many things, but then we have to have a process to check things. It was interesting to see Professor Marino showing that AI could be applied for borehole classification where you have cores to get the DSI. But then if we do that, we will need some process to correct if there are any mistakes or for any kind of estimation of parameters, we will need to have a process to correct or see if there are any mistakes. Again, with surrogate models, I've seen some examples in civil engineering, mostly in foundations. I've been impressed with the results. So I would say that they're definitely a good tool to be considered for design purposes.
Thanks. Anyone else like to comment? Phil?
I think AI is, obviously the opportunities are massive, but I think if the data going into the models, like any model, if that's not reasonable data, then I don't think we can ever expect to get a better answer out. And so even for the core logging example, if you don't have the correct markup of the core losses, depth measurements, etc., you apply the AI learning to that and you try and correlate it with other geophysical tools or whatever other interesting data set you might have from the same borehole. When the two don't match up, AI can't resolve that either, or it will make some inference with that data, but the data aren't in the same space, so it's not the right data. So I think we've got to get the first principles right and then build on that with AI and other good models and making informed decisions from that.
So you'll still need your engineering judgment to analyze your AI outputs. Is that what you're saying?
Well, I don't think you can't take the thinking away.
No, totally.
The thinking has to happen at the beginning and at the end. Maybe the AI automation can help with managing data efficiently, but the thinking can't go away.
Yeah, thanks. Neil, any comments?
Yeah, look, I agree with Phil. I don't think anyone in this room is going to be out of the job because of AI anytime soon. Like, I think there's lots of repetitive tasks and things like that AI can help us with. So, televiewer structure picking, for example, or even with shape metrics, automated structure orientations, things like that. But it won't take the thinking away. You still have to validate these things that the software did the right thing. So I don't think anyone's going to be looking for work or needing a secondary IT degree.
Thanks. This is a really good question that's come in. Considering closure projects, how can long-term time-dependent risks, such as greater than 200 years, be incorporated into model uncertainty and geotechnical assessment? Phil, I'll go to you first because there's done a lot of work in mine closure.
Yeah, I'll jump at that. I suppose 200 years is the upper limit. So LOP have just completed guidelines for mine closure, and part of that work, we thought long and hard about what a reasonable design life should be for open pit and waste dump closure. So we landed on 200 years as a reasonable number that you could reasonably defend a design service life up to that point. So beyond 200 years, I think you're asking a lot. Then you start stretching into a lot more guessing and less reliable outcomes, certainly. So I just don't think expecting people to design for service life more than 200 years is just too big a stretch to land on.
Any other comments from the panel?
Actually, I want to add one drawback of risk assessment of slope stability. This is there is that step where you need to involve stakeholders or decision makers to explain them what is the risk, what is the consequence, and then they have to bring decision whether you can apply or if they want to accept that risk or no. In deterministic approach, something like that doesn't exist. So basically, you use some flow rules, some standards, factor of safety value, and you produce your design to the stakeholders. So this is why I think that risk design is not so frequently applied in geotechnical practice, even though we as engineers don't understand completely this probabilistic design. We cannot expect from the stakeholders to accept it and to understand it. So this is another, I think, drawback that we should work on in the future.
Well, just to add on to that as well, I suppose material degradation over time, to try and probabilistically incorporate that into a design, I don't know how we'd even start with that.
It's even hard to do empirically with case studies, let alone in some sort of model that's updated over time, I think.
Okay, I'll go to a more general question now, but who funds the ISRM and what does it inform provide?
I think we need to check the website for that. But generally, it's funded to an extent by the national groups that form part of it. But please check the website.
Thanks. Any questions from the audience? Matteo, did you have one? No. Any other questions from the audience? And go to Neil. I'll go to Neil, Andreas, and then Vadim.
Hi. So I really enjoyed Vadim's presentation earlier. And one of the things he, I guess, had was as increasing knowledge in projects and pits got to a point where I guess the uncertainty got down, or the certainty in parameters got to 82%, and that was as good as it was going to get. I would ask a question of you guys: what level of uncertainty should that number be, and how does that evolve as technology evolves and we learn more?
Well, I think to an extent, as Phil said earlier, it depends on the client, whether it's a mining company or a civil construction site, on their risk appetite and how much risk they're willing to accept and how they can then manage that. Vadim's presentation was very insightful. I think that's something we need to certainly incorporate into the commission. But yeah, it's looking, these are some of the world's most researched mines, and they're hitting 80%. That's it's going to be hard to beat that, I think.
Yeah, I really enjoyed Vladim's presentation as well. I suppose with the way gold price is at the moment, I think you'd be looking for 100% reliability. Keep that ore road open.
Thanks, Andreas.
Thank you. I'd like to circle back on the AI discussion before. I mean, there's a lot of wishes that people think that AI can solve for us and some miracle things. So I'd like to ask back, what do you think? I mean, the major problem around that is to find enough training data for such a machine learning model, especially if we don't have cases that are comparable. How realistic do you see this kind of application being, let's say, used in a regular manner in the near future? How would you think on that this is in a reliable use? Because the major problem is to get enough training data out of that.
I'll have a kick. I think it's up to us to decide what the question is.
The question is, do you think that is realistic that an AI model is in a regular use in near future?
Yeah.
Because everybody speaks about AI, and I think a lot of people don't know how to reach these goals really.
No, absolutely. But I think it's up to us to decide what the question is. What question do we want to ask of AI? If we wanted to design a slope from scratch, then we probably have to wait something beyond our lifetime. But if it's a question about helping streamline the data flow on calculating fracture frequency on drill core or something like the question needs our expectations of AI needs to be tempered with what the robust data that we have. So I think it's up to us to have the pre-thought onto what we expect our outcomes to be.
Okay, good. So maybe I should have been more specific. I was thinking on slope stability analysis. Like I asked the AI, is this going to be stable or not? And I just point on a certain spot of the slope and said, make the rest. That's this. Sometimes I have the impression that's the expectation that people ask on machine learning. I'm not sure if this is realistic. That's my question.
I mean, I think it's a great question, but I agree with you. I don't think it's realistic. And there's, like I say, that's probably beyond our lifetime that might be realized. But there's other data sources that we don't have now that might be available at that point. I think that's asking for rock vision that doesn't exist yet.
But maybe we could use monitoring data more frequently. So instead of it being a reactive tool, there's a lot of monitoring data available that AI could probably be run over as predictive tool. So it's not saying just looking at a slope, a photograph of the slope, but if we have more proactive monitoring or background monitoring, we would be able to see the early detector signs of potential instability.
Well, certainly for hazard maps. Yep.
So just following on from what Phil said, again, I don't think anyone's going to lose their jobs in our lifetimes over this, but I think, I think it was John Harrison who once said, if rock masses were transparent, we'd all be out of the job. I don't think AI is ever going to tell us what's in the ground and then therefore be able to predict anything that could happen. Certainly not anytime soon. I think we need to really get better at site characterization, and that's always going to be a gap, reducing the data gaps that we have inherently because we're drilling small holes at quite large spacing, typically.
Vadim?
Yeah. Now with such great advances in numerical modeling, don't you think it's time now to move away from the criteria which we normally use, the instability criteria, the factor of safety and probability of failure, and move to those ones which quite often offered by the numerical modelers? It's could be numerical velocity or volumetric strain or horizontal displacements. Typically, that's what we get from them. And only they produce the factor of safety if the client asks for that. So maybe it's just the numerical modeling specialists can educate or put some kind of guidelines, maybe in LOP, because it's probably time to review it. It's 15 years old now, and put a chapter how to interpret in a more modern way of numerical modeling results.
I'm going to ask the panel to respond to Vadim's question, considering that we spoke about data uncertainty previously. So taking that into consideration on how accurate our numerical models are, but to then move forward with some of the different strain-based failure criterion, etc., as a different measure of stability or risk than factor of safety.
I'll have a quick go. I suppose to get those models right, though, there's a number of parameters that are pretty difficult to get right. Modulus, etc., and anisotropy, all those other parameters that are quite challenging. I suppose if we can get those numbers right, then that those design approaches can be a lot more mainstream. I suppose to your question about time for an update, the update of the 2009 guidelines is already underway. The plan is for LOP, hope to have that done by the end of this year. So that Reed and Stacey guideline will have a new version 2026.
So we can expect quite an extensive discussion on the numerical modeling results and how it's applied.
Yeah, so the instructions from the editorial group has been to the people that are contributing to the various chapters is to not rewrite what was there before, but to really be focusing on what's changed since 2009 to now. And obviously numerical modeling has jumped in leaps and bounds. So that is a key area of focus, as well as on the design acceptance criteria, having singular deterministic approaches, and now bringing in confidence consequence to those design acceptance criteria as well.
So I guess I think you're referring a little bit to the slope design methods chapter as well. So that one's evolving as we speak, and there's a lot of focus on DFNs and doing probabilistic analysis using different iterations of DFNs. That's sort of been one of the main additions so far since the 2009 one, and that's being headed up by Joe Cavallo from WSP Golder. So they're adding a lot of that in. Certainly, there's a bigger move towards 3D analysis in there, trying to help people with interpretation of that. But I mean, it's a 40 or 50 page chapter. It certainly won't cover everything. But agree with. I think this is another topic that needs to get looked at.
Harry, Zoran, any questions or comments?
Yes, I would like to also make a comment. What do you think parameters that you mentioned, are they like site specific or they can be used globally? Because factor of safety and probability of failure are, let's say, global factors. So
yeah, do you mean the weighting factors which we used for the different data types?
You mentioned the
ones, the numerical model, the numerical velocity, the volumetric strain.
Yes. So can you apply?
Yes, we definitely, yeah. And that's what, when for example, we get the volumetric strain from the numerical modeling guys, I understand quite well that that's those areas where it's highlighted, it's greater than 5% or 0.5%. I can expect rock falls, or when they provide the numerical velocity values, I understand that there is a potential for the big failures. But this is something, I am a geotechnical engineer, but this is something very difficult to convey to the management. And they still expect only one single criterion, which is the factor of safety.
But is this maybe related also to the rock type, to the brittleness of the rock? It's not the same if you are dealing with soft rocks, maybe brittle rocks. So can that criterion become universal?
But that's what the mine managers believe. It's universal. It's the only one they understand. Doesn't matter what sort of failure is, but that's something. It's up to us, up to the numerical modeling specialists to provide them the different guidelines and to make some sort of, to understand what sort of failure you can expect, what kind of the criterion you can expect to apply to your mine. But everybody expects just factor of safety. And everybody sticks to that number, 1.2 or 1.3. And that's one Phil is saying it's not prescriptive in the LOP, but people believe it's prescriptive because it definitely defines that table is, everybody's got that table on the wall.
Right. The design can still be serviceable and fail and have a factor of safety less than 1. If from a mining perspective, not a civil perspective, if you can still get the ore out safely, a failing slope, provided it's managed effectively, can still meet the business objective. So it's not just one number that must be achieved at all times.
But that's about quantifying the risk as well. You have to know, you don't want to be sitting on, I'm in the greater than 1.2 and it's going to be safe, but you want to quantify that, yes, it's less than 1, but how do we then manage that risk appropriately?
Yeah, absolutely. So the failure mechanism then needs to be incredibly well understood, that the expected failure volume is going to be in this order of magnitude. If you've got that wrong and now the failure becomes something unmanageable, then that's when the general manager starts asking some serious questions. But those are things that the geotech practitioners need to have a very strong understanding. If we are going to propose different acceptance criteria, we need to be acutely aware of what the downside implications could be.
So managing risk really is in the design stage and the implementation, which would bring in monitoring. So do you see any increase in different monitoring techniques or instrumentation going forward to help us manage risk better? Or optimize our slopes or excavations better as well?
Look, I think the technology's never been better than it is today. I mean, we've got prisms, radars, satellite INSAR, everything's available for surface monitoring. I think where the industry might be, from an economical risk perspective, might be falling a little bit behind is subsurface monitoring. I remember when I started my career over almost 20 years ago, we had a lot of inclinometers and it was never fun, probing those and getting data, but we'd really find things early, things shearing or moving slightly beneath the surface before we saw it on the surface. So I think a key thing we need to do to be more proactive is look within the ground a little bit more. I guess there's probably a bit, things like shape accelerators are becoming more cost effective. TDRs are being used. Phil?
Absolutely. Again, it's got to be a risk-based approach. If in Vladim's example with single haul road and, like I said, the gold price the way it is, I'm sure that mine has some pretty good monitoring to make sure that there's early detection of anything.
5 radars. It's the most covered by radars, the mine in the world.
But to Neil's point, though, radars only give you the outward manifestation of the instability. That the early onset really comes from subsurface monitoring. And like Neil says, I think that's what we're missing, that early detection with subsurface monitoring and then using the radars to fill in the gaps on the spatial extent of the failures.
Any final questions from the audience?
No.
Maybe just one to finish off as a combination of a couple of questions that were received on Slido. But in terms of managing risk, the different tools and methods that are available, obviously we've touched on 3D and 2D, but also thoughts on discrete elements versus finite difference. Any comments on modelling type or method to analyse risk? Empirical, I'll throw that in there too.
My personal belief is you need to be as simple as you can. So we can apply discrete elements, 3D finite elements, but as we spoke, uncertainty is high. And at the beginning of my career, I've used 3D finite element modeling. I started using 3D, things like that. But now I base my designs usually on limit equilibrium and some kind of experience. So maybe this is not the right answer that you expected, but I think that we should combine, advancement and some experience in order to achieve reasonable solutions. So,
here, with regard to the distinct fracture network, how we managed to get to have a distinct element code applied in a big, let's say, open pit mine problem. I think we need to gather a lot of information. Sometimes this is not feasible, or is realistically the amount of data that we might have is not enough to provide an accurate model. So it would be best to choose a model that is giving a result, 3D modeling with finite element with distinct structural elements, instead of doing a distinct element code with less accuracy. So usually we have to select between the most accurate approach, considering, of course, all the types of failures.
Thank you. Any final questions from the audience? If not, I'll go to one last one from Slido. Okay, final question of the afternoon. Society is uneasy when the terms risk and reliability are mentioned. What advice do you have for presenting studies to the public and regulatory agencies? I'd also say here, like risk. When you go for surgery, you're presented with what's the risk to the operation, or, when you're investing in something, what's the financial risk? How likely are you to lose money? So I don't think we as a society are immune to evaluating things in terms of risk. But as Vadim said, the management of mining, generally it is familiar with this factor of safety term instead of a probability of failure. But any comments on, reporting upwards or publicly risk?
I think using simple terminology must be the way to go. But that, like you said, Alison, that brings in other challenges that people don't understanding of what likely, probable, almost certain. I think there was a posting on LinkedIn a couple of weeks ago, and they polled a bunch of people asking what they thought probable, almost certain were, and they plotted these on a histogram, and the diversity of what people interpret likelihood might be is widely divergent. So I think when communicating those things, we need to be very simple and very clear on what those parameters mean.
Thank you.
Yeah, just following on from that, I think if we're, expressing things upward in a company or potentially even publicly, yes, we have risks, but we shouldn't just be presenting risks on their own. We should also be presenting what are we going to do about it. So some control measures and things we're going to implement to mitigate those risks and to move forward in the right manner. So they should be presented together, not just, we're going to scare you now. But so this is how we're going to manage things and put that out there for opinion.
Zoran, Harry, any final comments?
I agree completely with colleagues.
Well, thank you very much, everyone, for your participation. And thank you to the panelists. Please join me in thanking Phil, Harry, Neil, and Zoran. And look out for the outcomes of the ISRM chapter on risk and reliability. Thank you, everyone.